Everything we've been doing in the course so far has been focusing on measuring things. But the main reason we want to measure things as mechanical engineers is so that we can act on the information we get from those measurements to control something in the real world. So in this video, I'm going to talk about controlling things out in the real world from your Arduino. The obvious way to directly control something is with the digital input-output pins on the Arduino. There's 14 pins, and they can be set to either 0 volts low or 5 volts high with the pin mode and digital write commands. So that's a way you can have a direct effect on what's happening in the real world, is by controlling those outputs and causing those outputs to switch something on and off or make something happen. 6 of those outputs can do pulse width modulation, which means that they can switch really quickly between 0 and 5 volts to sort of look as if they are at some voltage in between. And that is accessed with the analog write command. And that'll allow you to run motors at part speed or dim some lighting or things like that. The big catch is that all of these digital input-output pins can source on the Uno a maximum of 20 milliamps of current. So there's not an awful lot of power there. If you want to drive something big, you're going to need to have some additional circuitry that will allow you to control a larger current than 20 milliamps. But for a start, what can you do with 20 milliamps? Well, 20 milliamps at 5 volts is about 100 milliwatts, which is really not much. You could power an LED and get a reasonably bright indication, but not enough to make a flashlight. It's enough to power a lot of sensors. You could power a Wheatstone bridge with it if the bridge had at least a 250 ohm resistance. And the ones you've used so far have had lower resistances. And it's definitely, and this is the really big one, enough to switch a transistor on and off so that you can control some of those higher current loads. One of the things you can use to control switching on a higher current load, even an AC load like a household current, is a relay. And this is a little relay on a circuit board designed to interface with some Arduino type controllers. It can switch on and off in here, and it switches mechanically. It's an electromechanically actuated switch. So it uses a solenoid to flick the contacts open and closed. Because it's a mechanical device, it's going to be subject to F equals MA and second order dynamics, so the switching time is not going to be really fast. And you don't want to switch it on and off really often. So this would be an on, then off type of switching. It gives you the advantage that it isolates the power side, these connections here, from the control side, because the control side is flowing through a completely different set of wires. So that's a definite safety consideration. But the coil in that solenoid draws more than the 20 milliamps that we've got available. So we'd need to use a transistor to switch it. And here's a sample circuit showing the solenoid with a flyback diode and a transistor that you can use directly from your Arduino outputs to do the switching for the larger current that's going to flow through that solenoid. And small relays show up in all sorts of automotive applications. And in older cars, this was pretty much the only device used for switching. So here's a little relay package in a plug-in box that would go into a typical automotive environment. And here's what you'd find inside. A coil with a whole lot of copper wire on it to produce an electromagnet. A switch element here that's pulled by the electromagnet, either up or down. And it moves from a normally closed contact, which will be in contact with the switching element whenever there's no current flowing through the coil, and a normally open contact that will be open, no connection almost all the time until you put some current through the coil, and then this switch will be pulled over here and it'll make contact right up there. So the advantages of using relays: once you've done the switching, the resistance in the current path, either through here to this contact, or with the coil activated through here to this contact, is just about 0. And other advantages, they're cheap and standardized. You can go out and buy them and install them and use them to control all sorts of different on-off type switching applications. The disadvantage of relays is you can't switch them on and off really quickly, and they are mechanical devices and they will be subject to mechanical wear and mechanical failure. If you go to solid-state devices like transistors, they'll allow you to switch really quickly, and they're not subject to that mechanical wear. There are no mechanical elements in them. And we've got another video that shows some more detail about these NPN transistors, about 25 cents each, that you can switch modest-sized loads on and off with. Or if you go to a larger load, big motor or a heavy lighting load, you might want to be switching a current more like in the amps range rather than 500 milliamps. These MOSFETs that I've got here will handle currents of up to 62 amps at low voltages and room temperature. So they're about $2. So also really cheap, typically cheaper than a relay. And you could use this MOSFET switching for really low current devices as well. But if you were really trying to save some money, you could go to a lighter duty switching transistor. So these technologies allow you to switch things on and off in solid state. Now, if you're switching on and off something like a relay or a motor or a solenoid, then the device you're switching on and off is an inductor. And as you'll find out in the electric circuits courses, inductors, current will tend to keep flowing. So if I switch it off all of a sudden, the current's going to try to keep flowing, and it's going to generate some voltage spikes. So as a result, flowing from 12 volts down here to the outlet, if this current tries to keep on flowing and I slam the transistor shut by switching off the signal, the voltage here will become very large. That could fry the transistor. We need somewhere for that current to go without it building up that high voltage and frying the transistor. Putting a diode in like this, normally this will be 12 volts and this will be down closer to ground, and the current will all flow through the inductor. But if I switch off this transistor, the current has nowhere to go down this way, so it would either build up a high voltage here, or because this diode allows current to flow in only one direction, that current that was being driven through the inductor can keep on flowing around in a circle here through the inductor until it dissipates due to the resistance of the inductor. So by allowing that diode to pass the current back up this way, we avoid the high voltage that's going to fry the transistor. This is really important, otherwise you'll burn through these MOSFETs in a real hurry. Maybe not immediately, but they won't last very long.